Hi students, in this video I am going to explain two problems that are based on chapter 2. Chapter 2 is about estimation of costs or engineering cost. So generally you will be given different components of the cost, and you will have to calculate the final cost of a product or the selling price of the product depending on the information given in the problem statement. So let's first focus on problem number 1. I am going to read this problem first, and then we will see how we can find the solution. The following data concern one of the most popular products of XYZ manufacturing. Estimate the selling price per unit. So we have been given the information regarding different costs, and we need to find out the selling price per unit for that product. Okay, so let's see what information we have on the cost. So labor cost is given, which is the one unit requires 12.8 hours of work, and labor cost is $18.75 per hour. Okay, 18, so 12.8 hours at $18.75 per hour. That is the labor cost. Then a factory overhead, that is direct. The first one is direct labor cost. Then the factory overhead. Factory overhead are basically for salaries of administrative people, engineers, managers who are not directly working on the part, but their salaries are also needs to be considered while you calculate the cost of the part. Right, so factory overhead. So that kind of groups all the different sorts of cost and salaries that you cannot directly apply to the part. So let's see what is the factory overhead here. Factory overhead is 92% of labor. So for each $100 spent on direct labor, 92 extra dollars needs to be spent on the overhead. Right, so 92% of labor. Then next item is material cost, that is $65.01. So that's material cost. Then packing cost is 10% of material cost. Cost for packaging is 10% of the materials cost. So these first four are cost components. Now let's see, we need to find out not only the cost, but we need to find out the selling price, or we need to determine the selling price per unit. So for that we have some other information. So this item is sales commission. So commission is sales commission for the per unit is 10% of selling price. So if we are selling the unit at $100, $10 is basically goes to sales commission, right? And the profit is 22% of selling price. So if you are selling something at $100, you are expecting $22 profit per unit. So let's see, now we need to calculate the selling price based on this information. First what we will do is we will calculate the cost of the product. Unless we know the cost, we won't be able to determine the selling price. So let's first look at the cost. Okay, so first element, labor cost, is, as we saw before, 12.8 hours per unit multiplied by $18.75 per hour, that is labor cost, and each unit requires 12.8 hours of labor. So if we multiply these two, we get the total labor cost per unit is $240. So that is direct labor cost. Next is factory overhead. Factory overhead, as given in the problem statement, is 92% of the labor cost. So we need to multiply $240, which is direct labor cost, multiplied by 0.92. So if we do that, we get factory overhead $220.80. That's the factory overhead. Next is material cost. Material cost is also given here, $65.10. So that we can put as is material cost $65.10 per unit. So that's given there. Packing cost is 10% of the material cost, right? So 10% of 65.1 is $6.51. Then so that's the packing cost. Now we have all the 1, 3, 4 elements. Let's find out the total cost. Total cost is basically the summation of these 4 costs, right? So if you add these 4 numbers, you get the total cost of $532.01. So that is the cost per unit, and we need to determine the selling price per unit, right? So let's see, let's assume that X is the selling price per unit, X. Okay, so X, and what is that? So if you write the mathematical expression for X, for the selling price, that will be something like let's see, selling price X is equal to, first we need to add the cost, which is 532.41. Cost of the cost per unit plus 10% sales commission, 10% of selling price, not 10% of the cost. So selling price is X, so 10% of X is 0.1x, right? 0.1x. Also profit we need 22% of selling price, not 22% of the cost, 22% of selling price, which is X. So 0.1x plus profit is 0.22, 22%, 0.22x plus cost is 532.41, right? So if we take these two terms, if we transfer them on the left hand side, X minus 0.1x minus 0.22x, you get 0.68x on the left hand side and 532.41 on the right hand side. Therefore X equals to 532.41 divided by 0.68. 532.41 divided by 0.68, the final answer, which is X, which is selling price per unit, is $782.96. So that's gonna be our final answer. Now let's focus on problem 2. Let's read the problem first and then we will work on its solution. So let's read the problem. British Petroleum recently completed construction of large refinery in Texas. The final construction cost was $28 million. The refinery covers a total of 340 acres. So so far we know that the cost of the refinery and the cost of the cost of the refinery and the size of the refinery, which covers 340 acres. We know that, right? The expansion and acquisition department at BP is currently working on plans for a new refinery in Oklahoma. The anticipated size is approximately 260 acres. The British Petroleum is now considering a new refinery in Oklahoma, and the anticipated size of that refinery is given to us is 260 acres. If the power sizing exponent is 0.72 for this type of facility, what is the estimated cost of construction? So basically we need to estimate the cost of construction for the new refinery that is going to be built in Oklahoma, right? We are given power sizing exponent 0.72. We know the size of the new refinery. The thing that we don't know is the cost of the refinery. That's what we need to determine, right? So in such problems, when we have two equipments, very similar equipments, only they differ in size, we can use something called power sizing model. Okay, power sizing model. That the mathematical expression is given here, and I'm going to explain that. But what it does is, if we know the two equipments, similar equipments of different sizes, and if we know the cost of one, and if we know the power sizing exponent for those type of equipments, then we can determine the cost of the another equipment, which may be a scaled up or scaled down as compared to the original equipment, right? So power sizing model equation is given here. C sub k divided by C sub x is equal to S sub k divided by S sub x whole raised to power n. Now let's see what are the different components in this equation. C indicates cost, okay, and S indicates size. N indicates the power sizing exponent, which is given to us 0.72. So N is 0.72. C is cost. Let's say K for Oklahoma, X for Texas. Then C sub K is the cost of the refinery in Oklahoma, which we don't know, right? C sub X is cost of the refinery in Texas. So cost of the refinery in Oklahoma divided by cost of the refinery in Texas is equal to size of refinery in Oklahoma divided by the size of refinery in Texas whole raised to power n. Right? That's the equation. This equation you can use it for any other problem with different equipments mentioned. The equation remains same. It's cost on one side and size on the other side of the expression, right? So C sub k, which we need to calculate, is equal to C sub x. So we are multiplying both sides by C sub x. C sub x multiplied by S sub k divided by S sub x whole raised to power n. Right? So now only thing we need to do is put values in this equation. C sub x we know that is $28 million. So that is $28 million here. S sub k is 260 acres. The new refinery is going to cover 260 acres anticipated size, right? Divided by the size of the old refinery in Texas is 340 acres. So that whole thing raised to power 0.72, which is power sizing exponent. So $28 million, if we calculate this term, you get 0.82436. 28 million multiplied by 0.82436 is $23,082,031. So that's the final answer. That's a C sub k. That's the cost of the refinery in Oklahoma. We determined that based on the other values: cost of the refinery in Texas, the size of the refinery in Texas, the size of the refinery, anticipated size of the refinery in Oklahoma, and N, power sizing exponent. Based on all those values, we calculate the estimated value for C sub k. Okay, so that is the problem number 2.